Hello everyone, today we're going to talk about continuity. So let's think about this. What does it mean for a graph to be continuous at a point or over an interval? So in other words, we're looking for no holes, jumps, gaps, asymptotes, anything like that. Okay, so what do we mean about continuity? Okay. A graph is continuous if you can trace over it and never pick up your pencil. Again, this is not the official, obviously, definition of it, but if you can draw it and not pick up your pencil, then it is continuous. So if you take a look at this one, here we have a graph. Where is this graph continuous? Well, obviously, if we drew this graph at this point in time here at -1, that is when it has a gap. So in other words, that's where the continuity breaks. So it is continuous over the interval -infinity to -1. You can either use a union or a comma, -1 to +infinity. Okay. We could also describe it as discontinuous at x equals -1. So let's take a look at another graph. Okay. This is at -1/2. Again, we still have a little jump here or a hole. So again, where is this continuous? From -infinity to -1/2. I'll do this one with a comma. Either way is fine. -infinity to +infinity because they are continuous through this portion and through to the left of it. Okay. So let's take a look at the next one. Is there any difference here? Okay, so you can tell we're going through all our different types of graphs that we might possibly see. So this one, yes, again, we have a gap or a hole here, even though it does have a function value at -1/2, where this one did not have a function value at -1/2. However, it still has a point of discontinuity. So again, it'd still be continuous from -infinity to -1/2, comma, -1/2 to +infinity, or we could also say it's discontinuous at x equals -1/2. Okay. All right. Where is this graph continuous? Hopefully you see it in this case here as well. This one is from -infinity to -1. So even though now the hole has turned into an asymptote, we have to pick up our pencil at that point in time. So -1/2, sorry. Union -1/2 to +infinity. So again, it's still continuous on these portions, but we have that asymptote there. Okay. And this one, we don't have to pick up our pencil at all, so it is continuous on the set of real numbers. As well as this one. -infinity to +infinity. Alright, so there's actually different conditions that have to be met for a function to be continuous at a point, and there are actually 3 of them. Okay, so what are these cases? And these cases are f of c has to exist, so the function value has to exist. The limit must exist as it approaches that value c. From again, the left and right hand side, they have to be the same, so the limit exists. And then the limit must also equal what the function value is. So please pause and write this down and continue when you are ready to do so. Okay. All right, so let's take a look at this next function. I want you to pause, and I would like you to use interval notation to describe the places that the function is continuous. Okay, so the first section here, -infinity to -1. Next section goes from -1 to +1. Again, we got a hole here, so it's discontinuous. Got to pick up my pencil. Third section goes from 1 to 2, because now I got an asymptote, and then it goes from 2 to infinity. And please notice that we're using parentheses with all these, and that is absolutely fine. There's no need to use brackets when we're talking about continuity. The next graph says describe the places that the function is not continuous and explain which of the three conditions is violated. So the three conditions would be function value exists, the limit exists, and then again the limit and the function value must be the same. So let's talk about this here where it's not continuous, and hopefully you see at the very first, just going left to right, we see here -4, I got to pick up my pencil. So the first one, it's discontinuous. Oops, discontinuous. So it's discontinuous at x equals -4. And which one is broke? Well, first one, it does actually have a function value. However, the limit from the left and the right-hand side does not exist because they're at two different places. So the limit as x approaches 4 of our function does not exist. So that's number 2 on our list there. Okay, so let's continue along. Where do I have to pick up my pencil again? Still, I'm okay here. I keep going, I keep going, I keep going. Boom, right here at 2. I have to pick up my pencil. And again, I have a function value. However, the left and the right-hand limit does not exist, so the exact same thing as we wrote right here. The limit as x approaches 2 of our function, should have equals in there, does not exist. So let's continue on. So we keep going. Again, here I have a whole, so the next value is at 4. And this one does not have a function value, so this is the first one. So f of 4 does not exist. Okay, so we're going to skip that next example. We're going to move on here to determine if the function is continuous at the stated value. So we're now going to look at our functions, not necessarily the graphs, which we were doing in the very first portion of it. And again, we have to check our 3 scenarios here. Our 3 scenarios. Does the first f of c, does that exist? So that's the very first thing that we're going to do. So I'm literally going to write, okay, 1. Does f of 4 exist? So I'm simply going to plug it in. 3 times 4 squared plus 4. And we get a function value, and this is going to be 52. So that exists. Second one, we now have to check, does the limit at f equals 4 exist? So we got to check, does the limit as x approaches 4 of our function exist? Well, again, with direct substitution should be the very first thing that we do, which is what we did in number 1. So yes, it does have a limit of f of 2. And then the very last requirement, if you recall, the limits, so 1 and 2 should be equal. The limit as it approaches that value and the function value should be the same. So yes, they are. The limit as x approaches 4 is equal to the function value of f of 4. Okay, so we would then say, therefore, and those 3 little dots mean therefore, f of x is continuous at x equals 4. Okay. All right, so let's talk about number 2. Again, we got to check those 3 requirements. So the first one we have here is, okay, function value g of x, not f of x, that should be g of x, at -2. If we substitute that in, we get 3 times -2 over -2 plus 2. And you can see in the denominator here, that's going to be undefined. Therefore, it is not continuous. Therefore, g of x is discontinuous at x equals -2 because it does not have a function value at that -2. Okay. All right, so again, we're going to skip the next couple ones there. We're going to move on to piecewise review. All right, find all points where the function is discontinuous and state the condition that is violated. Well, when we're looking at a piecewise function, what matters are these critical points. So we're looking at our domain restrictions here. So the first one that I'm going to look at is 0. Okay, so if I, again, go through my steps, if I check what is f of 0, if I plug it in, well, it would be equal to in our middle function here. So that's where we'd substitute that in. And we actually do have a function value there. So next we need to check the limit as it approaches 0 of our function. Well, again, we got to check the left and right end behaviors. Well, we've already checked the right end behavior with our function value, but we also need to check the left hand behavior. So the left hand limit would be approaching -3. The right hand, which again is what we plugged in step 1 there, we got a value of 0. Therefore, these are not equal, does not exist. So therefore, we know at 0, the function is discontinuous. So therefore, f of x is discontinuous at x equals 0. Okay. And then hopefully you realize too, we got still some more domain restrictions. Right away, we have a gap. This is 4, and then it picks back up at 5. So we don't even need to test that. We see we have a gap, and it's discontinuous on the interval 4 to 5. So right away we see that just from our gap there. Okay. Well, let's take a look at our next one here. Find all points where the function is discontinuous. Okay, so again, we have to look at our critical value here of 0. So let's go through our process here. And we have, so checking our function value at f of 0. So that would be -2 because that fits the domain restriction, so we're good there. Now we got to check our limit again as x approaches 0 of f of x. So the left-hand limit and the right-hand limit need to equal each other. Well, in this first part, where x was 0, we've got our left-hand limit of -2. And in this case, we need to do direct substitution. So 0 squared minus 2. Yes, we get -2. So our limit does have a value of -2. So we're okay there. Not sure what happened right there. That should be -2. And are these two equal? And absolutely they are. Oh, pardon me. So f of 0 does equal the limit value as x approaches 0. Therefore, it is continuous everywhere. So we can simply write, plug in my laptop here, therefore g of x is continuous. Erase that. All of a sudden it's writing a little bit odd. Is continuous everywhere. Okay, so this concludes day 1 of continuity.